Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to the lecture 4 of E207 Electronic Devices and Circuits. Today we will cover about electron and hole concentration in the semiconductors. You can say it's part 2, as in lecture 3 we also talked about that, but more for intrinsic semiconductors. Now we will talk about extrinsic semiconductors. So the content of these lectures are, first we will discuss briefly about extrinsic semiconductors. Of course we discuss about them in the lecture 2. Then we will talk about the temperature dependence of the carrier concentration, basically how the carrier concentration varies in a semiconductor. We will discuss about the band gap diagrams, we will calculate the Fermi energy levels for extrinsic semiconductors, we will calculate the carrier concentration, and then we will talk about the quasi-equilibrium situation. What is that and how does it affect the Fermi energy levels and how does it affect the carrier concentration. Okay, so if I just talk about the extrinsic semiconductors, as we know, we just talked about in the last few lectures about intrinsic semiconductors. In intrinsic semiconductors, charge carriers are generated thermally. Okay, so it is possible to change the carrier concentration dramatically by introducing these impurities in the crystal, and the process is known as the doping. So we can say doping is a process which introduces the impurities in the semiconductor, and these impurities are intentional. Okay, and it's not like that we can introduce any impurity. Of course, it has to be in the alignment what we want to make. For example, if you want to make an N-type semiconductor, which is rich in electrons, okay, or you can say electron dominating, mostly electrons basically, and p-type semiconductor is hole rich, dominated by holes basically. So when I say n-type semiconductor, I am going to introduce an impurity which will have extra electron, okay, and similarly for p-type semiconductor I am going to introduce an impurity which is having less number of electron. So therefore we have two different type of impurities. Now if you remember law of mass action, Ni square is equal to N naught into P naught, where N naught is equal to P naught exists. So you can say basically Ni square, Ni is equal to N naught is equal to P naught. This is the case for the intrinsic semiconductors, right? So one can say like what will happen in case of extrinsic semiconductor. Will this law of mass action be valid there? And what will happen to this N naught and P naught? Let's say these are the equilibrium electron and holes concentration respectively. So answer is that this law of mass of action will be valid in case of extrinsic semiconductor as well, and it might appear counterintuitive, but I will show that it is possible. And how it is possible, we will talk about it, why that law of mass action is still valid in case of extrinsic semiconductor, but the condition is that thermal equilibrium has to be maintained. So that's the most important condition. So this is valid under thermal equilibrium. Of course, same condition applies here in case of intrinsic semiconductor, that thermal equilibrium has to be maintained. But the thing here is that N naught is not equal to P naught. As we know that because of these impurities, number of electrons can be much higher than the number of holes in N-type case, and number of holes can be much higher than the number of electrons in case of a p-type semiconductor. Therefore, this is not valid, but this relation will be valid. Okay. So, provided there is a thermal equilibrium is being maintained. So, from this relation, if we know the level of impurity, we can calculate basically one charge carrier concentration. For an example, let's say it's an n-type doped, right? So, number of dopants, you can say number of electrons would be largely equal to the number of dopants, number of donor dopants. So, you can replace N0 with the value of the Nd, which is the dopant atoms, and then you can calculate P0. This Ni will remain same. Intrinsic charge carrier concentration. Basically, this is a function of temperature. So, if temperature is same, this will be same. Anyways, we will talk about that in detail. So, now the question comes like how these band diagrams looks like in case of extrinsic semiconductors. So, we will talk about that. Okay. So, let us say first discuss about the n-type semiconductor, where assuming we have, let us say, silicon lattice and few atoms are being replaced with group 5 element, either phosphor, arsenic or whatever you can use. And let me draw the energy bandgap diagram. Let us say this is my, so this is the case at temperature T equal to 0 Kelvin. So, we have E energy level, this is our conduction band, this is valence band, it's full of electrons, and here are also some free electrons sitting because of the dopant atom. And what happens in case of temperature, let's say T is around 50 Kelvin. So, these free electrons in this donor level will start moving to the conduction band. Okay. And similarly for a p-type semiconductor, if there are group 3 elements in a silicon, let's say lattice, boron, aluminum, gallium, indium, something like that. So, what will happen, let us say this is the valence band. So, this is the acceptor level. Okay. So, in this case, this is the case at T equal to 0 Kelvin. So, we have this acceptor level which is close to the valence band. Now, what will happen, let us say if you go to a slightly higher temperature T greater than 50 Kelvin, so some of these electrons can move to these levels, this acceptor level, and you will have the free holes here, and then electrons can move and can constitute the current. Of course, both need small thermal energy, which is relatively less than the case of a intrinsic semiconductor. Now, there is a one good question, that why these these donor levels and these acceptor levels are discrete, why they don't form the band, right? Like these are forming. We discussed about this in detail in lecture 2. So, the reason is that because they are too far from each other, because there are not that many dopants as compared to the lattice atoms. So, they are far from each other, they do not interact that much as these individual lattice atoms do. Therefore, these are in the discrete. Now, let me show you basically how the current happens in the case of extrinsic semiconductors. Let us say you have some lattice of silicon forming bonds. let's say this is boron and impurity. So this is the hole here, because it has only 3 electrons, so it can form 3 bonds. So the 4th bond is suffering here, it has a hole which is a positive charge. And let's say we replace another atom with some group 5, which is arsenic. So it will again form 4 bonds. Okay. Four bonds with silicon and 1 electron is free due to arsenic, and 1 hole is there because of the boron. And once, let's say, this electron is here, it gets some energy, which is, let's say, due to temperature 50 Kelvin, it can freely move, free to participate in the conduction, for conduction of the current. And similarly, these electrons can hop from here to here, so there will be hole here. Similarly, this can hop from here to here, the electron will move in another way. So you can say electron hopping is being taking place, which is constituting the current. So this is what it happens in case of an extrinsic semiconductors. Now if I talk about like how much is this level, the difference between, just we drew this, let's say this is conduction band, this is valence band. So how much is this level, the difference between EC minus EA? So of course it depends on the different impurity. So in case of silicon, group 3 impurity basically brings it to 0.003 to 0.006 electron volt. Sorry, 0.03 to 0.06. Okay. So 0.03 to 0.06 electron volt. And in case of germanium, this is much lower, 0.01 electron volt approximately, group 3 impurity. So EC minus ED, and this is EA. So this is EA minus EV. So I was giving some numbers for group 3 element, which will make it a p-type semiconductor. So you can see that these energy levels are significantly lower, 0.03 or 0.01 electron volt, while the band gap level for silicon is 1.12 electron volt. So this way impurity can significantly increase the conductivity of the semiconductor. Okay. So if I just give an example of a silicon where intrinsic charge carrier concentration Ni, just because of the thermal energy, you can say at room temperature is 10 to the power 10 centimeter per centimeter cube at room temperature. Now same increases to 10 to the power 15 if we introduce 10 to the power 15 arsenic atoms per centimeter cube. And this is just the atom, so unit is per centimeter cube. So then it will dramatically increase. So you can say 5 orders of magnitude increase is there by doping. So this way doping can significantly increase the conductivity by bringing extra number of electrons or by bringing extra number of holes. Okay. And a slight amount of temperature increase can dramatically increase. So that's the benefit, and that's why you can say this doping is so popular in case of the semiconductors, and most of these devices are on the based on these dopings, electronic devices. So if I talk about like in binary case, like 3-5 compounds, so elements from column 6 can come. For example, in case of gallium arsenide, okay, sulfur can come. Similarly, in case of 2-6, other elements can come. So having higher electrons and having less number of electrons, depending whatever you want to make, p-type semiconductor or n-type semiconductor. Okay. So now another thing is that different impurities will have different levels, like different donor level or different acceptor level. So that you need to keep in mind what kind of impurity you are doing. Depending on that only, there will be the energy difference. And there can be some elements which can provide two dopant levels or two acceptor levels. Just to give you an example, copper, a doping of copper in silicon has two donor levels and two acceptor levels basically in the forbidden energy gap. So now if I talk about the carrier concentration, how I can calculate that. So if you remember, in the previous lecture we did calculate all these concentrations using a simple integration of these energy states and the probability of their occupation with respect to the energy, and we did the integration for the whole band. And as we discussed in the last lecture that these electrons follow the Fermi-Dirac distribution function. So in case of intrinsic semiconductor, we were able to get this relation, okay, and where NC is represents your energy states in the conduction band. Similarly, NV represents the energy states in the valence band, and EI is the intrinsic energy level, which is exactly in the middle. So let's say this is your EC, this is your EV, and this is somewhere exactly in the middle. So EI is equal to EC plus EV by 2. If you remember, we also mentioned that the Fermi energy level will also be close to EI, but Fermi energy levels are not exactly in the middle. The reason is that even in the case of extrinsic semiconductor, as you can see here, so if Ni is equal to Ni, so Nc should be equal to e raised to power Ec minus Ef. If I replace Ei with Ef, Kt equal to Nv. So if you will solve it, you will find that only in case of Nc is equal to Nv, then only your Ef will be exactly in the middle. But the effective mass of electrons and holes is not equal, therefore Nc and Nv are not equal. So usually Fermi energy level is slightly distorted, slightly up or down. Now what happens in case of extrinsic semiconductors? This Fermi energy level shift is significantly high, okay. So in conduction band it will go up to this level. Let's say in case of n-type semiconductor, this is EC, this is EV, and similarly in case of a p-type semiconductor it will go significantly down. This is EEC and this is my EV. So this is p-type semiconductor. Sorry, this is p-type semiconductor. So as the Fermi energy level gives you the probability, right? We discussed about that in detail in the last lecture. It is obvious that it will shift up for case of n-type semiconductor, and it will shift down for n-type p-type semiconductor. So let's say irrespective of that, wherever Fermi energy levels move, Ei is being replaced with Ef here in these relations which we derived in the last lecture, and using this same relation just to see the link between the equilibrium hole electron concentration and equilibrium hole concentration with respect to the intrinsic charge carrier concentration, which is Ni. Ni is same. So Ni is same, either it is an intrinsic semiconductor or extrinsic semiconductor. It is same. Okay. So N0, if we just use this relation and if we remove Nc and Nc from these, and we'll get this relation. As you can see here, Ec is common, which will be subtracted, so Ef minus Ei. And similarly here, if we just remove Nv using these two relations, we will get the relation between Ni and P0 in terms of Ei minus Ef. Ev is common here. So you can see the difference between Ef and Ei, the Fermi energy level and the intrinsic level, the shift, this shift, basically this shift, you can see if I draw Ei here, so this shift you can see directly depends on the equilibrium hole concentration. And similarly, this shift in case of a p-type semiconductor directly depends on the hole concentration, equilibrium hole concentration. So if you know this, you can calculate that, or if you know the equilibrium Fourier concentration of electrons and hole, you can calculate the shift in the Fermi energy level from the intrinsic energy level. Okay, so this is interesting. And if I just do some, as I was just saying, like you can calculate the difference. So you can take N naught by Ni here. Okay, it will become N naught by Ni. And if you take the log on both sides, this you will lose this exponential. It will become EF minus EI by KT equal to log of N naught by Ni. And if you multiply it with KT, it becomes KT log N naught by Ni, and EI can go there. So from this expression, you know EI initially, K is a Boltzmann constant, T is the temperature, N naught and Ni. Okay, so you can calculate the Fermi energy shift, basically the new Fermi level of the Fermi energy level. Let's say this is your EI and this is your EC and EV. So this shift for the Fermi energy level can be calculated based on the, and of course N naught would be equal to your ND, number of the donor atoms. And similarly for holes, you can calculate that if you want, like minus sign is there because in case of p-type semiconductor it will go down. So EI will be higher than the EF. So there is a minus, this factor is being subtracted from EI, and similarly in case of a p-type semiconductor, this factor is being added to the EI. So I hope this clearly explains what is happening here. Now similarly you can calculate that in sense of if you want to do in terms of energy state, NC and NV. So in that case you don't need to take out these NC and NV, you just use this expression, the second one which we just discussed, this one, and you can calculate EF in terms of EC and EV with respect to the NC and NV. So if I draw these curves, what I get, let's say if I just want to draw with respect to doping ND or NA, ND is of course the donor atoms and NA is acceptor atoms. This is my energy level EC, okay, and let's say this is EV. So if let me draw me like line this. So let's see how EF changes basically. So EF, as you can see from this relation, will increase with increase in the whole electron concentration. So initially let's say it was somewhere in the middle, not exactly in the middle, or can slightly upset you can say. So it will go this way. EF will go up with increasing concentration of the donor atoms, and similarly EF will go down if we increase the acceptor atoms. It will get closer and closer to the valence band. On the contrary, it will go closer to the conduction band if we increase the carrier concentration. So you can say this is for your doped n-type doped case. This is the case for your p-type. Now another question you can see you can observe what happens with respect to the temperature. What will happen when temperature is increasing? So it is evident from here that EF minus EI difference is directly proportional to the temperature. KT is equal to EF minus EI is equal to KT log of N naught by Ni. So what does it indicate? This difference is increasing. So okay, so now what we'll do is like we'll see the temperature dependence of these extrinsic semiconductors or intrinsic semiconductors, like how the behavior changes with respect to the temperature. I hope it is clear, like how does this Fermi energy level shifts with respect to the doping. So the temperature dependence is very, very important basically. So Ni, the intrinsic charge carrier concentration, is this is what we derived in the last lecture. So it depends on the effective masses of electrons and holes, it depends on the band gap, the energy band gap difference, and it do depends on the temperature, but it doesn't depend on the doping, no dependence on the doping. Okay, so no role of doping is here for the Ni, and that's why you can say this law of mass action, Ni square is equal to N naught P naught. So Ni is basically at any room temperature is a definite number for a given semiconductor and is known for the most materials, you can say, and Ni can be used to calculate N naught into P naught using this law of mass action. If I draw a curve, like if you want to see how this concentration will behave with respect to the temperature, let's say this is my temperature and this is your N centimeter per cube. So the curve is something like this. This might be a bit confusing why something like this is happening. So let's discuss what is happening. So initially, for initial range, this can be, of course it do depends on a large number of parameters, approximately let's say 100k. So initially it needs some thermal energy, right? So based on the thermal energy, number of N will increase, because we know that they are either in the valence band or at the donor level, and they need some energy, either it is an intrinsic case or extrinsic case. In case of, in this range, over a range of temperature, let's say, sorry, this has to be dotted, so up to 500 Kelvin approximately. So during this range, semiconductor can behave like an extrinsic semiconductor, because temperature is enough for electrons to jump the barriers. Okay, and afterwards what happens, that the temperature is so high, this is sort of a breakdown region, and huge number of electrons will cross the barrier. So that's why the relation goes something like this. Initially it goes gradually, basically it takes a thermal energy and then it saturates for a while, for a good range of temperature, you can say, and then if temperature goes more than that, it gets so much energy that the N will increase dramatically. But of course we are not going to deal in that temperature range, we will be working in this temperature range where it is known as the extrinsic region, where it needs some energy, the electrons goes there and Ni remains stable for over that range of the temperature. Now the good question is like how these like electrons can be drawn, electron concentration can be drawn. If you remember, we drew this curve with respect to energy. So now we'll do it for an N-type semiconductor here, in this case N-type semiconductor. So let's say this is a valence band, EC, this is conduction band, okay, and this is my donor level. This is, let's say, ED. Now, and this is my E. If I want to plot it, this is Fermi energy level and this is my E. Okay. So if you remember, in the case of intrinsic semiconductor, it used to be a symmetrical curve. In the last lecture we discussed very symmetrical curve. Just ignore my bad handwriting. It used to pass through somewhere in the middle. EV, EF, right? But that is not the case here, because we know that the Fermi energy level is no longer in somewhere middle. So we'll just see how is the case, and we know that the Fermi energy level is somewhere close to EF, right? Obviously it has to be close to EF because it shows the level above, below, above, below all are filled, and above which none is filled at T equal to 0 Kelvin. But of course that's not the case, because we are not discussing the T equal to 0 Kelvin case here, a room temperature. So it shifts up because number of electrons are more now in the conduction band, and this goes something like this. So if I just calculate the number of electrons, it will go something like that. So in n-type case I am talking about, this is my E, C, okay, and this is my, so you can say the number of electrons in an n-type semiconductor is of course much higher. The probability of their occupation is much higher, and that's why, because energy states are same, number of energy states, number of energy states are same as in case of a intrinsic semiconductor, but probability of their occupation is not same. Probability of occupation is not same now, not same, and which is being described by the Fe, which is Fermi energy level. So you can say it is fairly up in the case of a n-type semiconductors, and this region is significantly large than this small region here in the valence band. Okay, so now we will see the case of a p-type semiconductor, how it goes in the case of a p-type semiconductor. So in p-type semiconductor you have this conduction band, you have this valence band, okay, and your acceptor level is somewhere here, EA, your EC, EV, and now we know that in case of a p-type semiconductor your number of holes will go dramatically high. So it will be something like, if I just draw PE, let's say, and this is your number of electrons, this is my EC, this is my EV, okay. And if I just draw the Fermi energy level diagram here, this is somewhere here, okay. So this will have a very small probability here, and probability will increase, sorry, I will just delete this one, okay, yeah. So this is, sorry, so this is EC, let's say, and this is EV. So you can see this probability is significantly higher, 1 minus Fe in this case, probability of occupied states. So number of holes are much higher in case of p-type semiconductor, which is also indicated by this. So basically not much difference, but just it's that the introduction of the acceptor level, introduction of the donor levels is there, and also your Fermi energy level shifts up and down. We have seen that with respect to, and this shift of Fermi energy level will be depending on your dopants or the acceptor atoms. Higher is that, higher would be the shift. So now we will see how it looks like. Let's say if we have to draw a band gap diagram of an n-type semiconductor, if we draw all the levels together, and let me give an example of a silicon case which has 10 raised to power, let's say 16 arsenic atoms per centimeter cube. So this is something like your conduction band, this is your valence band, okay, your intrinsic energy level is somewhere in the middle, so it has to be straight actually. Just that was my bad handwriting. So this comes out to be 1.12 electron volt. The band gap EZ is equal to 1.12 electron volt. Now EF, your Fermi energy level, is somewhere here. Okay, and your dopant level is somewhere here, ED. So for this particular case of silicon, where the band gap difference is 1.12 electron volt, and with a doping of 10 to the power 16 arsenic atoms per centimeter cube, just to give you some idea, this difference between EC and ED is approximately 0.05 electron volt, and this difference between the shift in the EF and EI is somewhere around 0.035 electron, or 358 electron volt. So don't get confused that the dopant energy level will be equal to the Fermi energy level. No, dopant energy level is for the atoms which are free, more free. In case of n-type doping, they are sitting there, so new energy level is there, and Fermi energy level again gives the probability. Okay, so now let me just draw everything together, how it looks like. A case of n-type, case of intrinsic semiconductor, case of a n-type semiconductor, and case of a p-type semiconductor. So that will give you a better idea. Okay, so let me just draw for the case of intrinsic semiconductor. Okay, so this is your EC, this is your EV, and this is somewhere in the middle. Okay, this is EV, this is EC, this is E, and this is somewhere in the middle, let's say EI. And if I draw the Fermi energy level, so symmetrical and passing through the middle, EF. So this is this is, let's say, EC, and this is EE, and it is symmetrical. Basically, the most important identification, if you have to identify if this level is given, E versus Fe probability of their occupation is given, then you can identify it using, if it is symmetrical, that's the intrinsic semiconductor. And if I just draw the carrier concentration, let's say this is hole, this will be something like that. This is electrons, these are electrons, and this is your holes. Both are of same size. So N naught is equal to P naught, Ni square is equal to N naught equal to N naught into. So this is the case of the intrinsic semiconductor. Now what happens in case of extrinsic semiconductor? Let's see. This is EC, this is EV, and here it shifts little up, and these energy states will remain same. So they will remain same. It doesn't change in case of a n-type or p-type or whatever it is. So they will remain same. But this Fermi function will change. Fermi energy level will shift little up, so it will be somewhere here, and this will not be symmetrical any longer. If I just draw in the middle, so as you can see, it has already shifted. This was EI, let's say, initial one. So it is something like this. It passes through here and comes here. This is 1, let's say. So probability of free holes is much lower than this one. Now if I just if you just calculate the carrier concentration, the electron concentration, it will be significantly larger here than the case of EV. Significantly larger. So you can say N naught is much larger than the case of. Similarly, you can draw it for holes. Oh, sorry, P-type semiconductor. This is for your N-type semiconductor. So energy states are same. The only Fermi energy shifts up and from towards the conduction band from the middle, and that gives a large number of electrons. And similarly, you can do for the holes. It will shift down, and the number of holes would be much larger than the number of electrons in case of P-type semiconductor. I hope you could get some idea. Now you can draw the band gap diagrams, you can draw this Fermi function, you can draw this carrier concentration with respect to the like bands, which band has how much carrier concentration. Okay, so now we'll talk about another type of a semiconductor, which is degenerate semiconductors. And here your law of mass of action doesn't hold. Okay, so you might ask, what is degenerate semiconductor? So it is the case where Fermi function, Fermi level, lies inside the conduction of the valence band and the material is degenerate. In such case, exponential approximation to the Fermi function cannot be used, and this is the case where the very heavy doping has been used, and so that you can say very heavy doping so that your band actually donor or acceptor impurity band actually merges with the conduction or the valence band. Okay, so it is so high that there are so many free electrons and so many free holes are there. So in such situation, these semiconductors are known as the degenerate semiconductor, and this law of mass of action, law of mass action doesn't hold. Cannot use this one. So this is something you need to keep in mind, but of course for most of the course we will be dealing with the standard extrinsic semiconductors only. So this is just to tell you the one situation what will happen once the we have basically too much doping. Okay, now very important thing, quasi-equilibrium carrier concentration. So far we have been talking about law of mass action as valid in case of extrinsic semiconductors as well, or intrinsic, as of course in the case of intrinsic semiconductor, but we have always put a condition that thermal equilibrium has to be maintained. Okay, so what happens if it is not being maintained? Will this law be valid or not? And what will be the energy levels? That we need to look into that. And now in this part of this lecture, we'll talk about that. So what happens when we say quasi-equilibrium situation, in which conduction band electrons, let's say this is your conduction band, and the electrons in that band, and let's say hole in the valence band, they are mutually, the electrons within the conduction band are in equilibrium, holes are in equilibrium, but electrons and holes are not in equilibrium. Electrons and holes are not in mutual thermal equilibrium. So you can say electrons and holes are not in mutual equilibrium, but electrons within conduction band are in thermal equilibrium or in equilibrium you can say, and similarly holes are within valence band are in equilibrium. Okay, but electrons and holes are not in equilibrium with respect to each other. Individually they are in equilibrium. So you can say when this situation will arise, let's say when external current is there or a flux of photon is there. So how does it happen and what are those circumstances? So as I said, there is some external force which takes the electron from valence to the conduction band, okay, and this equilibrium is being disturbed. Electrons get busy within the conduction band. So it arises when the relaxation time for transition within each of these bands is much shorter than the time it takes to move from conduction band to the valence band. So intra-band relaxation time is on the scale of 10 raised to power minus 12 second, while this radiative electron and hole recombination is on the scale of 10 raised to power minus 9 second. So electron moves from the valence band to the conduction band, it gets busy there in different transitions, and the transition time is much lower than the time in the radiative transition from conduction band to the valence band. So in such cases it is appropriate to use separate Fermi function for each band, separate Fermi function for the conduction band and separate Fermi function for the valence band. So because since electrons and holes are not in mutual equilibrium, they cannot be represented by a single Fermi function. So you can say two separate Fermi functions are required since electrons and holes are not in equilibrium. They cannot be represented by a single Fermi function, and these are represented as EF, C and VF, V. And these are known as the quasi-Fermi levels. Right. So these Fermi energy levels EFC and EFV lie in the conduction and the valence band respectively, and the concentration of both electrons and holes can be quite large. So take home message from here is that if you want to calculate these concentrations and all that, you need to first keep in mind what is the state of the semiconductor, whether it is in thermal equilibrium or whether there is an external driving force. So things can be very much different. Also you can see these Fermi functions separately decides the population of electron in the conduction band and the valence band, and it has been displaced from the equilibrium, and this displacement is being caused by this electron voltage or the exposure to the light energy. And since the recombination rate, the rate of equilibrium between bands tends to be much slower than the energy excitation rate within each band. So this rate of recombination is much slower than things are happening within the conduction band and the valence band. So there is a mismatch. So therefore equilibrium case cannot be applied, things will be different, and this situation is known as a quasi-equilibrium. So how they look like, let me just draw it for you the Fermi energy levels in such case. Basically, give me a second, let me draw it for you. So again we will draw this conduction band and then the valence band, EC, EV. Okay, so as I said, now we have two separate functions. So in case of, let's say, conduction band in first case, so there can be large number of free electrons here. So this goes something like this. This is your E and this is your F of E, and let's say somewhere probability of distribution is okay, and your Fermi function is somewhere here. So we are not concerned about the valence band any longer. So this Fermi function now is giving the probability of their occupancy within the conduction band. That how it is behaving within the conduction band. And if I just draw it by another function for the case of valence band, this comes out to be EV, and in this case it will be something like this, and let's say this is 1. Okay, and if I draw the concentrations, carrier concentration on the x-axis, this will look like something like this. So they don't need to be same. As you can see, EC, EV. So two separate functions, okay, and the conditions are that there is some external force, whether in case of current or in case of photon flux. Intra-band equilibrium is there within the band. But not between two bands, okay, not interband. Within two bands there is no equilibrium. That's why we have these two separate Fermi functions. Okay, I hope you could understand about the quasi-equilibrium. Now last thing that we're going to discuss in this lecture is the compensation and the charge neutrality. So what happens, let's say, if you have a semiconductor where you do have some p-type doping, some n-type doping, how to do the some mathematics here. So charge neutrality is very, very important. If the material has to be or is remain in electrostatically neutral, the sum of the positive charge holes and ionized donor atoms gets the positive charge because they are giving electron, must balance the sum of negative charge. Okay, electrons plus the acceptor atoms, because they accept the electron, that's why they get negative charge. So the equation can be written like this. This is, you can say, equilibrium concentration before doping. This is because of the dopants, where these are the donors and they get the positive charge because they are giving the electron. Similarly, this is the number of electrons in equilibrium before doping, and these are the acceptors atoms which accepts the electron. So let's say if I just draw a diagram where both are there, both acceptors and the donor atoms. So this is somewhere in the middle, EI, this is your EC, this is EV, and EF is somewhere here. So as I have drawn EF above the EI, from there you must get an idea that ND is greater than NA here. Both are present, donors as well as acceptors, but number of the donors is larger than the number of acceptor here, and this is your So using this expression of charge neutrality, we can do a lot of stuff, basically most of the calculations, and then on the top of this we can apply the law of mass of action and we can calculate the concentrations. So today we'll finish it here. If I just summarize what I discussed today, we talked about extrinsic semiconductors, why doping is so important. Dopant can make a lot of difference. The shift in the band diagrams, basically new acceptor levels, new acceptor levels, new donor levels. Then we talked about the shift in the Fermi energy function. Okay, how this Fermi level shifts in case of n-type semiconductor, p-type semiconductors. Why law of mass of action is still valid, because this carrier concentration is not a function, is a function of basically temperature and band gap difference that we have shown, but the number of electrons is no longer equal to the number of holes. The number of electrons will go much higher than the holes in case of a n-type semiconductors, while in a p-type semiconductors number of holes will increase much larger than the number of electrons. In case of intrinsic semiconductors, number of electrons and holes are equal. So this is something we discussed in that case. We drew the diagrams. I hope you could get some idea. Then all these calculations are valid in case of thermal equilibrium. Then we discussed the case of the quasi-equilibrium state, where there are some external forces are there, electron current, voltage is being applied, or exposure to the light is there. So in that case, you can say we have two Fermi energy functions, two Fermi energy levels, and both are in the conduction band or in the acceptor level. So always keep in mind whether semiconductor is there, what are the conditions. The external conditions defines our layout. Thank you very much. See you in the next lecture. Thank you.